In this video, we'll discuss the dynamics of non-uniform circular motion. The figure shows a particle moving in a circle of radius r. In addition to a radial force component required for all circular motion, this particle experiences a tangential force component and hence a tangential acceleration. This acceleration is given by the equation a sub t is equal to dv sub t dt. If we look at the figure, we see our familiar radial force acting inwards that causes a centripetal acceleration, a sub r. But now we're adding a tangential force along the t-axis, and this tangential force causes a tangential acceleration, a sub t. Force and acceleration, of course, are related to Newton's second law. We can break the force law up into components. A radial component, which is the sum of the forces along the radial direction, is equal to the mass times a sub r, which is the centripetal acceleration, which is equal to the mass times the tangential velocity squared over the radius r, which we know is equal to m omega squared r. In the t direction, the sum of the forces is equal to mass times the tangential acceleration. And then perpendicular to that plane is the net force in the z direction. If there are no forces in the z direction, they sum to zero. Let's consider example 8.6, called sliding out of the curve. A 1,500 kilogram car drives around a flat 50-meter diameter track, starting from rest. The drive wheels supply a small but steady 525 Newton force in the forward direction. The coefficient of static friction between the car tires and the road is 0.90. How many revolutions of the track have been made when the car slides out of the curve? In this example, we'll model the car as a particle in non-uniform circular motion and assume that rolling motion and air resistance can be neglected. So here's a drawing of our example. On the left, we see from above, the car is going around following a circular path of radius r, and in any instant, its tangential velocity is v sub t, as shown. If we draw a three-dimensional force diagram, we show that along the radial direction, we have the static friction force, which is the source of centripetal force in this example. The car wheels are applying a force in the direction of motion, which we're calling F sub wheels, and it's in the t direction. Acting vertically downward is a gravitational force. In opposition to that, along the plus z direction, is a normal force. Known in this example is the radius of the circle, which is 50 meters, the mass of the car, 1,500 kilograms, the coefficient of static friction, 0.90, and the force being exerted by the wheels, equal to 525 newtons. So let's solve. So we want to find the angular displacement when the wheels begin to slip. So that means that the tangential velocity has gotten faster and faster and faster, associated with a greater and greater centripetal acceleration, since the centripetal acceleration is equal to the tangential velocity squared over r. So eventually, that static force, which is causing this centripetal acceleration, is greater than the maximum static force. So when is F sub s, which is equal to mv tangential squared over r, which is equal to m times r omega squared, when is that equal to F sub s max? Which we know is equal to mu sub s times the normal force. In this case, if we look at the free body diagram, the normal force is balanced by the weight. So we know that we can replace the normal force with the weight mg. So we have on the left-hand side mr squared, mr omega squared, and on the right-hand side mu sub s mg. This is an r here. So the omegas cancel out. I mean the masses m cancel out. And omega then is equal to the square root of mu sub s g over r. So we want to find out what that angular velocity is at that particular, after that particular displacement. Well, we know that analogous to our three kinematic equation for linear motion, we have three kinematic equations for angular motion. And our equation 3 is omega final squared is equal to omega naught squared, the initial angular velocity squared, plus 2 times the angular acceleration times the displacement, delta theta. And it's this delta theta that we're after. So this is a good equation to use, since we know that initially it started from rest, so omega naught is 0. And we also know that the angular acceleration, alpha, is equal to the tangential acceleration divided by the radius of the circle. And according to Newton's second law, this tangential acceleration is equal to the force exerted by the wheels divided by the mass of the car. So I'll replace that a sub t with f omega, fw divided by m, and I still have the r in the denominator. So we know what omega is. We can calculate it right now. It's equal to the square root of the coefficient of static friction, which is 0.90, times g, 9.8 meters per second squared. And we divide that by r, which is 50 meters. And when we calculate that, it turns out to be 0.42 radians per second. Okay. So now we're ready to solve for delta theta. Delta theta well, before we do that, why don't we go ahead and solve for alpha, since we have this equation right here. We'll put in the value of the force by the wheels, which is 525 newtons. And we divide that by the mass of the car, 1,500 kilograms. And also by the radius, 50 meters. And we see that the angular acceleration is 6.99 times 10 to the minus 3 radians per second squared. Now, delta theta is equal to omega squared over 2 times alpha, which is equal to our result for omega, which is 0.42 radians per second squared, that's in the numerator, divided by 2 times alpha, which we just found to be 6.99, times 10 to the minus 3 radians per second. And we do that, and we calculate that, we get a result of 2 revolutions. And that's the solution to the problem. So we'll adopt the following problem-solving strategy for circular motion problems. We'll model the object as a particle and make other simplifying assumptions, and visualize with a pictorial representation using the RTZ coordinates. In our visualization, we'll establish a coordinate system with the r-axis pointing towards the center of the circle and show important points in the motion on a sketch, define symbols and identify what the problem is trying to find. Identify the forces and show them as a free body diagram. Then we'll solve applying Newton's second law in the radial direction and in the tangential direction and in the z direction. We'll determine the force components from the free body diagram, being careful with the signs. The tangential acceleration for uniform circular motion is 0. Solve for the acceleration, then use kinematics to find velocities and positions. And then we can assess by checking our result for correct units and significant figures is reasonable and answers the question. In this quick check, a ball rolls around the inside of a horizontal pipe. The ball is fastest at the lowest point and slowest at the highest point. At the point shown, with the ball moving down, what is the direction of the net force on the ball? As we can see, the answer is choice D, because acting in the t direction, the tangential direction, we have the gravitational force acting down. And then acting towards the center of the circle in the radial direction, the normal force. So the net force is the resultant force between the gravitational force and the normal force.